Okay, so the next step in Umbral Calculus, before we get into some of the results that they came up with, is sort of understanding what formal power series are. It also helps to have a little bit of an understanding of generating functions, which we'll kind of cross paths with a little bit here, but this is enough just to get going. So the first thing is a very um, unofficial definition of formal power series. You start with a ring R, and you can get funky with this if you like. And I'm leaving a lot of stuff out here, but really all it is the coefficients of a series, okay, that you create are going to lie inside R. So it's going to look just like a power series, but you're just going to have coefficients within R. For instance, you could have something like Z with the double brackets X, and this is how you denote it. You use these double brackets, or where we're really going to work, which is R, right? And here we have a field, so we can do even neater things there. Um, and I guess my goal for this video is just to cover some algebraic properties of this. Okay, I'm not going to get too deep into stuff, but just some things you need to know. And the first thing, the most important thing is, for the purposes of Umbral Calculus, is that this is what they call an algebra. Okay? And if you're using a field here, R, it's commutative. It's a commutative ring, and more powerfully, algebra. But why am I saying the word algebra? Well, algebras are vector spaces, okay? These are vector spaces, but they have like a copy of the field inside of them. And so one way you could think about this is if you didn't have any x's at all, if you just had the constants r, they would live in this. You just wouldn't have any higher powers of x than 0, right? And it's clear to see, maybe I ought to make it more obvious here, that these things start at 0. Okay, so you're definitely going to have constant terms in here, and if you just leave just constants, you're going to have a copy of r. The fact that they are vector spaces implies that there's a dual space, and this is really where the majority of umbral calculus lies, okay, is in recognizing this dual space of what are called linear functionals. We'll get into that in a little bit. Don't let it freak you out. Another thing about this is you'll notice that this ring, this polynomial ring, it looks a lot like the ring of formal power series, doesn't it? I mean, these are polynomials with indeterminate x, and these are formal power series with indeterminate x. And really, the way that I write this is, this is the set of stuff that looks like this, finite, right? With coefficients in R. And here's the set that looks like this, right? So it's pretty clear that these things are sets of each other, right? Or this is a subset of the ring of formal power series. Maybe one thing to note here is maybe the biggest blaring difference between this and the ring of polynomials is that there are inverses for some of these elements in the ring of formal power series that are invertible. Okay? And so let's figure out what that might look like. Well, let's take this one. This is a formal power series, going to go on to infinity. And let's multiply it by something with coefficients that are labeled with b's, plus yada yada yada. Okay? And let's force it to equal 1. Okay? Well, I can expand this out. I have a0, b0. Now I'm going to collect terms here. So what do I have that's going to give me 1 power of x? Well, I could multiply a1x to the first by b0. So b0 a1 plus, I could do A0 plus B1, okay? I'm just collecting terms here, and that's going to give me this and blah, blah, blah. And it actually, there is a nice little form for this, which we'll come back to later. It's just the sum starting at 0 up to, I can use n, of a sub k times b n minus k, and that's going to be the coefficient of x to the n, okay? But the point is, I'm claiming that this is invertible, okay? And what that means is that on this side, okay, I have 1 and I don't have any x's. So that gives me this series of equations that seem very similar to things that you probably run into in linear algebra, why you would want linear algebra. Now, assuming that I was given all my a values, okay, I can solve for b0. It just means that b0 is 1 over a0, okay? Right? I'm just dividing both sides by a0. And then I take this thing here. What does that have to equal? Where there's no power of x to the first on this side, so this term has to equal 0. Okay? So b0 a1 plus a1, I'm sorry, a0 b1 has to equal 0. And look, I have my b0 here, so I can plug this in. I have a1 over a0. I'm just plugging in b0. a0 b1 is 0, and now I can solve for b1, and so on and so forth. And I continue to do these equations using this formula here. Right? And I can solve for every single one of these b's. But notice that this only works, the only thing I really need is that this is true. This is the only thing of substance. It's easy to have stuff equal 0. It's not so easy to have it equal a real constant. And the one way you absolutely can't have this happen is if a0, which you're given, is 0. And so the invertible series are precisely, sorry about that. Anyway, is that this multiplication has to be 1, which means that a0 has to be non-zero, okay? I can find a b so that this works as long as a0 isn't 0. So these elements where you have some constant term in your formal power series are invertible in this ring. And obviously, in the ring of polynomials, there are no invertible polynomials. You have to do some funky stuff to get there. Another interesting thing about this ring, is that it has ideals, okay? Has ideals. And the ideals look like this. So if you think about what this is, you're just taking all the formal power series and multiplying by x to the k. And so maybe we introduce this little piece of notation called the order of f, where f is in this ring of formal power series. And this is just the lowest power of x with non-zero coefficient. Okay, so for instance, if f equals, let's say f equals 1 plus x squared plus yada yada yada, then O of f is 0, because the lowest power of x here is x to the 0. Similarly, if f is x squared plus x cubed plus yada yada yada, the order of f would be 2, right? Because this is the lowest order of x, okay, with a non-zero coefficient. And you'll see, if you just think about it for a second, that this is the exact same thing. This ideal, writing this, is the exact same thing as just considering series that have at least order k, right? Um, they're the same thing, all right? You'll also notice that this kind of gives this weird nesting thing where you can start with the big papa ring, right? And then you can kind of work your way backwards based on the power of x that you choose for your ideal, dot, dot, dot. You continue to get higher and higher and higher in powers, and you could see very clearly that they're all nested within each other. And since these are the only ideals, that means that this bad boy right here is maximal. You could actually prove that it's maximal very easily by just considering what the quotient of these two things is. That's all formal power series with everything power of x or higher sent to 0. That's just going to be your constant term. So you cover all your constants, that's r. Okay? And since this is a field, this is maximal. Since this is maximal, it's prime. And so you can even do a localization here. And it winds up being the same damn ring, which is kind of interesting. This is not usual. This is not what you would normally see. But yeah, that's pretty crazy. So I'm trying to think if there's anything else that should really cover. Maybe. Oh, yes. Hang on. There's one other thing that's kind of important. Okay. So you could see there's one dynamic of looking at this, where we can multiply these things together. Okay, and maybe we need to talk about what happens to order when you multiply. Okay, so there's one way you can treat these series. Okay, is if you have f and g in this ring of formal power series. Okay, you can multiply them. Okay, this is one thing that you'll look at, and you'll think about this. What's going on here? And one thing that we know for sure is that when you multiply them, their orders are added. Okay, so this also gives more evidence that those ideals have to look the way that they do. But another thing that you can do is you can consider the algebra related to substitution, or another way of saying that is composition. And this is really where we develop some interesting algebraic properties, because we get a group, but we consider things that look like this, f of g. And what I'm going to cover in the next video is this interesting theorem called the Lagrange inversion theorem. And it's a way of finding, given f, find g such that f of g is x. So in other words, f and g are compositional inverses. Very interesting stuff here. Okay, the idea of Umbral calculus, I'll just say this, the upshot of this whole thing as it relates to Umbral calculus is that this ring of formal power series has a dual space of linear functionals, because it's an algebra, it's a vector space, so it has a dual space of linear functionals that can act on this. And that goes back to that example I gave, Rhoda's example of the Bell set, or the Bell polynomials. And this is pretty huge, because what we're going to consider are linear functionals. And then we're also going to consider linear operators. That also live in one of these two spaces. And so what we'll wind up doing is just calling this P, and then this P star, but they're the same thing. Okay, and so these linear functionals and linear operators live in this ring of formal power series. And maybe one last note about this. You can, oh boy, that's hideous. You can get like a field of fractions like thing here. And you can you can see that this is actually, it lives in something bigger, much, much bigger, called the field of formal Laurent series. All right. So there is an extension to this where we can get into a really nice field, and you can think about it. We do have some invertible elements, but a lot of them are going to be in these non-trivial ideals where they have zero constant coefficients, right? And so what you'll have to do to get into this field is kind of divide off the lowest power of x, and then you'll have something invertible, and bada bing, bada boom, you can make it go. That's pretty much all I want to say about this. We'll work on Lagrange inversion theorem next.